Hello everyone. So today we are going to start a new chapter. It's chapter 10, graph theory. So first of all, what are graphs? It is not plotting x versus y. It's not plotting an equation or an inequality that you may have learned in calculus courses. It's a different kind of model. Graphs were first described by Leonhard Euler, a mathematician, to solve the Königsberg bridge problem. And then after that, they have been used to model problems in mathematics, computer science, engineering, like electrical or electronics engineering, chemistry, social science, urban planning, all these different areas. So let's first understand what's the definition of a graph. So a simple graph, especially an undirected simple graph G, is defined by two sets V and E. V is a non-empty set of vertices and E is a set of edges. Each edge in this case is an unordered pair of vertices from V. So a graph is defined by its vertices and its edges. For example, let's take V equal to A, B, C, D, F. That means in this graph there are 5 vertices A, B, C, D and F. And E is the set of edges. There are 5 edges we can see. So that's the graph. Let's try to draw it. So the vertices, you can draw them as a little bit of points here, B, C, D, E. So try to name them A, B, C, D and E. These 5 are our vertices. And the edges are AC. So let's put a line between A and C. Then BC, AD, DF, so this one's F, and CD. So this is our graph G, determined by V and E. Now you don't have to draw these vertices in a circle. You can draw them any way you want. For example, you can draw it like this. So A, B, C, D, F. And the edges are B, C, C, D, D, F, AC and AD. So that is also a valid way of drawing it. Remember, the drawing of a graph is one drawing. For most cases, or for all the graphs that we are going to learn in this course, the graph itself is independent of the drawing. You can draw it in this way, you can draw it in this way. You just draw the vertices as points and then you draw the edges as lines connecting those points. Okay, so that's the first type of graph, undirected simple graphs. Undirected simple graphs or just undirected graphs are used to model different objects in computer science. Most of them you are familiar with. For example, networks. So each of these vertices can be a computer and there is an edge if these two computers are connected by an Ethernet cable or through the internet. Social networks. So each of these vertices can represent one account, and if these two accounts or these two people are friends, then you put an age between them. So for Facebook, it's like A is friends with C and D but not friends with B. You can use it to model road networks. So these are cities and there are highways in between them, or these are junctions inside one city and these are the roads. You can model them for airline routes. So these vertices are airports, and if there is a flight between them, you can put an edge. World Wide Web. So these vertices are web pages, and if there is a hyperlink, you can use the edge to represent it. So you see there are many different problems in real world where we use graph theory or graphs to represent the underlying mathematical model. So that's why they are very useful. Let's look into the other type of a graph. It's called directed graphs. So directed graphs, it's the same thing. It's a set of vertices V, a set of edges E. The only difference here is each edge is an ordered pair of vertices. So for example, let's take this graph where V is A, B, C. So A, B, C. These are our vertices. And E is, first edge is A, B. Since they are ordered, to represent the order of the vertices inside that edge, we use an arrow. So that's the difference between undirected graph and directed graph. Every edge has a direction. So AB is represented as an arrow from A to B. Next one is BA, B to E, then AC, and the other one is CB. Okay, so these are our 4 edges in this directed graph. Again, you can draw it differently, like so A, B, C, A to B, B to A to C, and C to B. Again, where you want to position the vertices is your choice. Which way how you want to draw the edges, it's your choice. The only thing you have to make sure about is you label all the vertices and you label all the edges, their direction correctly. Directed graphs are used to model call graphs. So let's say these are 3 people, A, B and C. If A makes a call to C, it can be represented as an edge from A to C. So for A it's an outgoing call, for C it's an incoming call. So call graphs. Module dependency graph. So let's say when you are installing a software in a new machine, or you have written a program that has different modules. So there are dependency. One module can only work if the other module is present. So that's why this module dependency graph is there, and it can be represented using a directed graph. Protein interaction graphs in biochemistry and some other social networks like Twitter is directed graph. So Facebook is an undirected graph where if 2 people are friends, you just put an undirected edge or just a line segment between them. Because if A is friends with B, then B is also friends with A. But in Twitter, it's different. There is a direction. If A follows B, then you can represent it as a directed edge from A to B. And if B follows A, then you can represent it as an edge from B to A. For example, here we have a directed edge from A to C. That means A follows C. That does not guarantee that C follows A. And that's why there is no edge from C to A. So now that we learned about the definitions of what is a graph, what is vertex, what is an edge, let's learn some more terminologies in graph theory which will be really helpful to describe certain concepts in this chapter. So if E is an edge U, V, where U and V are vertices in a graph, it can be directed, it can be undirected. We say that U and V are adjacent or neighbors. So if two vertices U and V are connected via an edge, then they are adjacent or they are neighbors. And E is incident to the edge is incident to those vertices U and V. And those two vertices are called the endpoints of the edge E. Then, in a simple graph G, the degree of a vertex V is the number of edges incident to V. So, let's take the first undirected graph, for example. So, this is our graph. Let's try to find out the degree of these vertices. So, let's make a table V and degree of V. So we have A, B, C, D and F, 5 vertices. For each, let's see how many degrees do they have. So A has 2 edges, so degree is 2. B has 1, similarly C 3, D 3 edges incident to it, and F 1. Similarly, for directed graphs, the in degree of a vertex is the number of edges going into V, and the out degree of a vertex, denoted by degree plus V, is the number of edges leaving V. So let's draw this table. We have V and in degree and out degree. So we have A, B and C. So for each, let's count their in degree. How many edges are going into that vertex? For example, A, this edge is going in and that's it, 1 edge going in. For B, there is this edge going in, this edge is going in, so 2. And for C, only this edge is going in, so 1. For out degree, how many edges are going out? From A, there are 2 edges going out. For B, 1 edge is going out, 1. Okay, so now we know the in degree and the out degree of each vertex for a directed graph. And the last one, generally we use the letters or the variables n and m to denote the number of vertices and edges in a graph. Generally, it's not a thumb rule. Generally, we prefer these two variables n and m to denote the number of vertices and edges in a graph. Next is the first theorem, Handshake Theorem. This is a very important theorem, Handshake Theorem, that involves degree of vertices in a graph and the number of edges. So in an undirected graph, G with vertices V and edges E, if you sum up all the degrees of all the vertices, then it adds up to twice the number of edges. Okay, so we have this one example of an undirected graph. If we check it, then we'll see how to prove it. Okay, so if we add all of them, 2 plus 1 plus 3 plus 3 plus 1 is 10. So summation of degree of V is 10, and 2 times the number of edges is 2 times, how many edges are there in this graph? 1, 2, 3, 4, 5 is 2 times 5 equal to also 10. So it checks out. Sum of all degrees is 10, twice the number of edges is 10. Okay. For a directed graph, sum of all in degrees is equal to sum of all out degrees is equal to the number of edges. So let's do that. It adds up to 4, this adds up to 4. So sum of all in degrees is 4, sum of all out degrees is 4, and how many edges are there? 1, 2, 3, 4. So this also checks out. The sum of in degrees is equal to the sum of out degrees is equal to the number of edges. So this theorem, the results, they look correct. If we try to prove it, it's a simple proof. The proof can be summarized easily, that for each edge or every edge E, that can be defined as U comma V, it adds 1 degree to the vertex U and 1 degree to the vertex V. So every edge adds 1 degree to U and 1 degree to V. For example, let's say this edge AC. So this edge, it adds 1 degree to A and 1 degree to C. Similarly, this edge AD, it adds 1 degree to A, 1 degree to D. So every edge adds 2 degrees in total, one in one endpoint, another one in the other endpoint, because every edge has 2 endpoints, and that's why the sum of all degrees is 2 times the number of edges. So to finish the proof, so each edge adds 1 degree to one endpoint and 1 degree to another endpoint. So all these edges adds 2 times E degree is in total. So sum of all degrees equal to 2 times E. Okay. Similarly, for the directed graph, every edge adds 1 in degree to one vertex, 1 in out degree to the other endpoint, other vertex. That's why the sum of all in degrees is equal to sum of all out degrees is equal to the number of edges. Next is theorem 2. An undirected graph has an even number of vertices of odd degree. So to prove that, let's try one example first. So we keep the example from the first undirected graph example that we just learned. So to use it, let's first write down the degrees for each of these vertices, as you remember. So A was 2, B is 1, C is 3, D is also 3, and this is 1. Okay. So in this graph, number of vertices is denoted by n, which is 5. Number of edges is denoted by m, which is 1, 2, 3, 4, 5 also. Well, this is the example we are using. Now, we defined that V is the set of vertices. Since we are dealing with the set of vertices with odd degree and even degree, we need to use some names for that. So let's say V1 is the set of vertices with even degree, and V2 is the set of vertices with odd degree. What does that mean? That means in this example, what are the vertices with even degree? That means the degree is an even number. So A has degree 2, so A has even degree. So in this example, V1 consists of only one vertex, A, and all these other vertices B, C, D and F, their degree, that number itself is an odd number, so they have odd degree. So in this example, V2 is B, C, D, F. So what are we trying to prove? We are trying to prove that an undirected graph has an even number of vertices with odd degree, and V2 denotes the vertices with odd degree. So we are trying to prove that the size of V2 is an even number. So the goal is the size of this set V2, which is the set of vertices with odd degree, is an even number. That's our goal. So let's see. What do we know? We know that if we add the degrees of all these vertices in V1 plus if we add the degree of vertices of all the vertices in V2, what do we get? That means we are adding up all the vertices in V, all their degrees, and using the Handshake theorem that we just learned, we know that this adds up to 2 times the size of the E, which is 2 times M. So this is an interesting equation. 2 times M, M is an integer, so we know this is an even number. Now if we look here, this is the sum of all the degrees of V, where V belongs to V1, and V1 is the set with even degree. That means all these degrees, all these terms that add up to this number, they are all even numbers. So this summation is a sum of even numbers. So if you take a lot of even numbers and if you add them, we know that is itself an even number. The sum, the whole thing, is an even number. So in this equation, this term plus this term adds up to this term, and this is an even number, this is an even number. So what is this term? This has to be even. If this is odd, odd plus even would be an odd number. So this has to be even. So that even plus even is even number. So now we know that this value, the whole thing, the sum of all degrees in of V, where the vertex belongs to V2, which is the set of vertices with odd degree, that sum is even number. We still have not proved. We still haven't proven that size of V2 is even. We just have proven that this adds up to an even number. Okay? But what is here? All these degrees, they itself are odd numbers, because V2 is the set of vertices with odd degree. That means all of these degrees, they are odd numbers, like 1, 3, 3 and 1 in this example. So these are all odd numbers, and we are saying that they add up to an even number. So each term is odd. Each term or each degree here is odd, and they add up to even. So there are a lot of odd numbers here, and they add up to even. Now we know that if you take two odd numbers and if you add them, you get an even number. If you add three odd numbers, then you get an odd number. If you add four odd numbers, then you get again an even number. So the number of terms, that means the number of these degrees, or how many vertices are in V2, which is our goal, how many vertices are in V2, has to be even. Because only an even number of odd terms can add up to an even number. Again, to clarify, only an even number of odd terms can add up to an even number. If you add an odd number of odd numbers, then it will be an odd number. If you add an even number of odd numbers, then it will be an even number. So this has to be even, and all the terms are odd, so the number of terms or the number of vertices in V2 has to be even, which was the goal. So we have done our proof. So the last one, some comments, some notes about the maximum and minimum degree and number of edges for a given graph with n vertices. So if a graph G has n vertices, then the max degree is n minus 1. So what is the maximum degree? So given any vertex V, how many other vertices can it be connected to? So the graph has n vertices, so for any one single vertex it has n minus 1 possible neighbors, n minus 1 other vertices, and at max it can be connected to all these other vertices. So that's why the maximum degree is n minus 1, where the minimum degree is 0, a vertex that is not connected to any other vertices, a vertex that does not have any edge incident to it. It does not have any neighbor. And the second one is using this, the maximum number of edges. Given a graph with G with n vertices, what is the maximum number of edges you can draw? So that calculation can be done from here. So the maximum degree is n minus 1, and how many vertices are there in total? N vertices. For each, the maximum degree can be n minus 1. So the maximum summation of degrees can be n times n minus 1. And from the Handshake theorem, we know that the number of edges is half of it. In other way, you can also write it in this way. N choose 2. And this is an idea from combinatorics that you have already learned. Each edge is represented or can be represented as a pair of vertices. So how many vertices are there in total? N vertices. How many possible pairs can you choose from that? N choose 2. So n choose 2, or n times n minus 1 over 2 edges you can draw in a graph. Minimum number of edges. That's easy. You have a graph with n vertices. There is no edge. You did not draw any edge. So the minimum number is 0.